What we're searching for today is very simple. It's the answer to how do we decode the wonderful code that we created just about, a week ago now, something like that. Let's just remind ourselves where we were with this code. It was a 5-bit code. Coding theorists will talk about this code, which I'm going to write out, as being a 5-2-3 code. I'll fill in the details and then I'll refer what I've written down to this. Remember also that these are the exact powers of 2. That's 2 squared. The number 2 position is 2 to the power 1. The number 1 position, well, that's 2 to the power 0. But that leaves bit 3 and bit 5 for the actual message bits. 2 bits, bit 3, bit 5, 2 bits, 4 combinations possible. And those were the 4 San Francisco weather states. So I've sometimes referred to these as info bits, message bits. It comes to the same thing. That's the message you're trying to get across. That's the message that these parity bits are there to check out and make sure it's okay. And we ended up with one code word, if you remember. That's the in phrase for these things. The 0, 0 state in message terms, I think we said was foggy this time around. And here's the protection of the parity bits. There we are, all written out again now. Coding theorists would call this a 5-2-3 code. How does that work? Well, it's a 5-bit code. That's what the first number means. It means total number of bits. The 2 means the number of message or information bits. And this, if you remember, is this business called the distance. How many bits differ between these rows? So the distance, in the technical usage of the term here, the number of bits that differ between that line and that line is 3. And to get one of these codes working, you need a minimum distance of 3. And what do we mean by working? What we mean is that a distance 3 code can correct a 1-bit error. And for those of you just yelling at me, but what's the general formula then for what you can correct for a given distance in that? Watch carefully. It's a one-liner more or less. Floor of d minus 1 over 2. And remember, floor of means round down. So let's do it for distance 3. 3 minus 1, 2. 2 divided by 2, 1. Round down 1, it's already rounded down. So that's telling you. Using the floor of function, it's saying for distance 3, you can detect and correct 1 error. So bearing that in mind, if we see things in the future with different distance properties at the end, we can always apply this to find out how many things they could correct. The powers of 2 and the parity check bits, what sequence of numbers were they used in checking up on? This first block, the 1 bit, checks itself and 3 and 5. 2 bit checks itself and 3. And the 4 bit checks 4 and 5. Where do those come from? How do you get those lists? And I think last time I perhaps didn't make this quite crystal clear. So let me explain that those come from effectively saying, for all of the things that aren't powers of 2, how could you build them up from adding together powers of 2? 1, you don't have to build it up, that's itself, 1 is 1. Similarly, 2 is a power of 2, and it's just itself. Where you really have to start doing this powers of 2, add them together to build them up thing, is with 3. The most compact way to represent 3 as sums of powers of 2 is 1 plus 2. What about 4? No problem, 4 is itself, it's a power of 2. But then when you get to 5, you say, the most compact way to do this is 1 plus 4, powers of 2. 6, 2 plus 4. 7, quite complicated now, but if you think about it, sum of powers of 2 that add up to 7 in the most compact way you can do it, 1 plus 2 plus 4. So really, these lists that we had previously about what checks for what is as a result of writing these out first and then say, but if we were going backwards, where does the digit 1 appear? It appears in itself, it appears in the formula for 3, it appears in the formula for 5, it appears in the formula for 7. So that's where that first list came out here, that 1 checks up on 1, 3, 5, 7, 9, 11, all the odd numbers, because 1 would appear in the sums of powers of 2 that build those up. 2, yes, 2 appears obviously in its own list, but it appears first of all next door in 3 as being 1 plus 2. Does it appear in 4? No, 4 is all on its own, it's a power of 2. What about 5? Would 2 appear in 5? No, it's 1 plus 4. So the next place that 2 would appear is 6, which is 2 plus 4. So I hope if you...
So if you had a 6-bit code, would 2 have to check on...
On 1 extra bit? Yes, it would. Similarly, 4 checks on 4, it checks on 5, it also checks on 6, because 6 is 2 plus 4. So if you're building up these lists and making them longer to do more complex codes, then if you're encoding and decoding in this by hand method, you need to keep up to date your sums of powers of 2 for all the new positions, unless they're exact powers of 2, and then go backwards and say, but these are my checklists that I build up from that. So just to remind you then of what happened was that on this one here, let's take this second one, the information or message bits are 0 and 1, but it tells us here, that's bit 3 and bit 5, but it says here that bits 1, 3 and 5 taken together must be even. Well, 3 and 5, 0 and 1, add them together, that's 1. So therefore bit 1, which we would be filling in, has to be 1, make it even. We're going to say, because you all want to know how to decode it and detect errors and correct them, this one here is going to be badly transmitted. Instead of 1, 0, 0, 1, 1, it is received as 1, 0, 1, 1, 1.
So straight away, whoever gets that is going to say that isn't right.
They're going to say that that isn't right because there's so few of these, there's only 4 of them. You get to know them like old friends. But you imagine if you got 64 of the so-and-sos, can you guarantee that you'll be able to memorize every single one? No, you need an algorithm. And what we do here is a reverse of what we did when we encoded. We say, let's look at the list that follows on and is checked from 1, 1, 3, 5, and so on. That's what we received. Bit 1 is 1, bit 3 is 1, 1 and 1 is 0, bit 5 is 1, 0 and 1 is 1. It's supposed to be even parity. Wrong. It came out as odd parity. Bit 2 checks out on itself and on bit 3. It doesn't occur in bit 5 because 5 is 1 plus 4, not 2 plus 4. So you look at bits 2 and bits 3. 0, exclusive ORed or added, if you like, to 1. It's a 1. It's odd parity. It's wrong. Okay? Now you look at the 4 bit and you say bit 4 checks out 4 and 5. 4 and 5, 1 and 1, it's 0. Hooray! It passed the test.
Yeah, we failed 2 tests. We can work out from that now.
Yes, you can.
What's gone wrong?
Very simply, because the headers of these lists are the powers of 2 that they check up on in all of those lists. And if the 2 one has gone wrong and the 1 one has gone wrong, then the wrong bit was 1 plus 2. Ordinary addition this time, not binary addition. 1 and 2 makes 3. Bit 3 is wrong.
So then we flip bit 3 and we've got the right code.
You flip bit 3. 1, 0, 1, 1, 1. That's the bad bit. It's received as a 1. It's wrong, so it must have been a 0. 1, 0, 0, 1, 1. Magic. Does that look familiar? That's what you correct it back to. And it's entirely done by getting these lists of powers of 2, doing another check on them, almost like it's exactly the same as when you were encoding. It's just you're doing it again. You say, that's wrong, it doesn't add up.
So you've simply reversed the process. I mean,
yes.
Does that always work then?
Yes,
For any of those bits, for the
For any
parity
of the,
bits as well.
now that's a good thing. If you're thinking, oh, but that's a message bit. Oh no, come on. Something really went wrong there because what was transmitted as 01, that's sunny, wasn't it? Has turned out as rainy 1-1, wasn't it? You turned to rainy. Oh yeah, that's fine. But what about if you hit a parity bit? Surely that messes everything up. No, it doesn't. It's actually dead easy. And I want to leave as an exercise for you to do is this time 10011. Don't hit a message bit, hit that parity bit at position 4. Change it to 0, do the checks, and you'll find out that the 1 list passes with flying colours. Nothing wrong with it. The 2 list passes with flying colours. The only one that fails is the 4 list. So if it's the only one that fails, that's it. 4 is 4. Nothing to add to it.
You've done the homework for them.
I've done the homework, but yeah. So do it for yourself on any bit you like and convince yourself that it doesn't matter if it's message bit or parity bit, this method will come in on it. I have built this up and I've explained to you now. You can go into a pub full of coding theorists and say, hey, like I've got this 523 code. And they will say, well, you realise that you derived it using Richard Hamming's algorithm, but it's not a true, proper Hamming code because it's not perfect. And you say, perfect? What's perfect? I think we have to go to another video, Sean. I know they hate cliffhangers. But yes, real Hamming codes are perfect. They really are. Now, the only sort of, if you like, slight health warning to say about this, just to round this off now, is by all means do it by hand. If you want to code it up as a program, great, you'll learn a lot. But don't run away with the idea that this is the most efficient way to do it.